Get started. Welcome to Purdue at Westgate First Tuesday event. My name is Samantha Nelson, and I'm the program manager for the Purdue Research Foundation, which manages this facility, and it's called the Westgate Academy. So make note of it so you can come if you haven't been here before. Make sure that you come. We have all kinds of different events that should be relevant to what you're looking for. So we try to bring together people on the first Tuesday of each month to design an opportunity for industry, academia, and government innovators to converge, share knowledge, develop networks, and have discovery opportunities. We want to thank Booz Allen Hamilton for sponsoring the networking event that will follow this presentation. They are a large defense contractor, to put it mildly, that has office space within this building, so we want to thank Booz Allen Hamilton for the food and drinks that we'll have afterwards. I just want to mention that we had someone come in the building last week and asked if we had heard anything about a microchip plant that was going on in Odin, Indiana. And I thought it was funny too. We kind of looked at him and said, I don't know, where have you been? What's been going on? And he said that he's asked everybody around here, and no one knew anything about a microchip plant that was being built here. So I thought that was funny, and we were so excited about what's going on, so we had to tell him all the information that we knew. And he said that was the most information he had heard about it, and he was so excited. Come to find out, I think he was part of a labor union that wanted to be able to help with the construction of the company. But to add to this excitement that we have someone who has been and will continue to be an integral part in supporting the microelectronic research presenting today. He is part of an initiative that will give students the opportunity to build and test microelectronics in extreme environments, training them for in-demand jobs while addressing critical defense and space industry needs. The project, a workforce ecosystem for strategic radiation hardening by design, is supported by a $5 million grant from NSWC Crane and additional support from the Indiana Economic Development Corporation. He is a new addition to IU as the Associate Professor of Intelligence Systems and Engineering. Let us now hear from Professor Daniel Lovelace on IU's strategic investment for innovation and their contribution to microelectronics.
All right, thank you, Samantha. Thank you for hosting me today. This is such a pleasure to be here. I have been at Indiana University for a solid 4 months, so I'm a veteran IU employee at this point. A lot of the new leadership at IU is actually pretty new as well, so sort of all in the same boat, so to speak. But it feels like I've been here a lot longer, and I think you'll see a little bit why. Presumably, you've seen some of these headlines over the last few months. It started out, so I started officially in August, and in July they started making announcements about our partnership with NSWC Crane, which of course was the $5 million award that Samantha was just mentioning. And then that sort of snowballed. So in September we had our kickoff meeting for the grant, and then all of a sudden we are seeing $111 million investments coming out of IU. And so what I'm going to do today is talk a little bit about what we're planning with those dollars and how we're going to make an impact. So, and this just, of course, continued and continued and continued. And then, of course, the one image that I want to show at the end of this is what's really happening at the ground level is that we've got very bright young people that are being trained on microelectronics and extreme environment microelectronics. They're going around the country doing tests of their designs that they're manufacturing that we are designing in the laboratory right here regionally, and these folks are entering the workforce right now. So, this is really at the core of what we're doing, and I'd like to always keep that in mind. So, the Center for Reliable and Trusted Electronics is housed in the Luddy School, so I wanted to spend just a second talking about what the Luddy School is about at Indiana University Bloomington. Well, really, we have two campuses. We have the Bloomington campus, which there's several Luddy buildings. This is the primary one. It's a beautiful glass building kind of contained within this limestone, this Indiana limestone. But we also have a campus in Indianapolis, which is where right now there's a computer science program. And so that's really going to be growing kind of our capabilities within the college. And I want to note that the engineering part of Luddy has only been in existence for 7 years. And that's a pretty important feature, and that's an asset in this case, as I think you'll see in a few moments from my perspective. But we were born out of an informatics program, which is a really interesting pairing. And the way I like to think about it is we now have an ability to talk about what we're doing in a beautiful way. And I think that's really critical for especially given some of these workforce challenges that I'm going to note. And then, of course, we have a high-performance computing capability that is really, really substantial, where we do a lot of artificial intelligence work. And that's being infused into what we are doing with microelectronics as well. So when you walk into Luddy, it's this beautiful open-air building. The lighting is incredible. It's very inviting to work in. And as you make your way up the stairs, you see this structure hanging from the ceiling. And so, sometimes you'll hear the structure moving. But you certainly will see it, and you'll see light reflecting all over the place. And this is a sentient piece of artwork. And they contracted with an architect in Toronto, I believe, and built this structure. At least the design firm kind of designed it and started installing it with help of our engineering students at Luddy. And there's thousands and thousands of microelectronics and embedded systems in here that have little motors and actuators that move this thing around. So the structure actually evolves. So you can physically hear it, but you can also physically see it, and it changes day to day. I think that this sort of embodies what we need to be doing in microelectronics to tackle the sort of evolving state of our system. So when it really is an ecosystem problem, not a process like we might like to think of engineering historically. So the Intelligent Systems Engineering program is within this college, and while it was established mere 7 years ago, we've attracted over $40 million worth of funds during that period of time, and within the last 4 months that I've been here, we've attracted an additional 10. Okay, to be kind of in perspective of the scale and the rapid evolution of microelectronics at Luddy. We have 30 current faculty, and we just, as of 3 days ago, announced that we are hiring 5 additional ones that are focused in microelectronics, but in partnership as well with chemistry and physics. So we're really trying to build a program that isn't just centered within our own college, but is a broad kind of perspective. And we have about 300 students currently in the program. At the undergraduate level, and quite a bit more at the graduate level. Okay, so for the remainder of this talk, I've kind of segmented it in these 3 parts where I'm going to kind of make an argument about the landscape of not just microelectronics, but extreme environmental electronics, especially critical for kind of the application space at present, right? The defense environment, the space environments, which is going to lead me to jump the gun there, the strategy, and then if I have time, I'm going to highlight one of the projects that one of the bright PhD students in my lab is working on, and which several of them are here, actually, if anybody would like to meet any of them. At least 4 of them are here today. Okay, so this is a slide that I co-opted from Matt Kay, who's one of the primes over at NSWC Crane that is supportive of the creation of our center, IU Create. And this sort of outlines the DoD microelectronics vision at a 100,000-foot view. It's about guaranteeing long-term access, first keyword, to measurably secure microelectronics. All of these are really important words. We could probably just talk about this sentence for a while. Guaranteeing, first of all, access is a problem in our current microelectronics market space. Measurably is becoming more of a challenge with the more complex these devices are getting. And then the security of them is becoming paramount, right? This is a visionary statement, and it pretty much sums up the entire challenge that we are facing. That being said, this is a pretty all-encompassing vision. This is sort of the template that we are going by when trying to realize our center at Luddy. So when I talk about mission-critical microelectronics, what am I talking about? It's not just space and defense. It's actually permeating in all kinds of market areas. So nuclear power, weapons, medical systems, and more we're seeing this be in critical automotive environments. In fact, the reliability requirements for electronics and automotive systems is actually more stringent than space and defense systems in some cases. And it's not that it's maybe more stringent, but the requirements are more clearly articulated. And we're learning a lot from that segment of industry. We're often inviting folks that work in this space to come to space conferences to help us understand how they do that now. And then also in high consequence IT, that's where our personally identifiable information is. So what I like to study, and I've been studying for about 20 years, are how does the harsh environment nominally in space systems, which includes a lot of radiation that's outside of the Earth's atmosphere, but we can consider that in other environments as well. How does that impact the integrity of our electronic systems? So for approximately 5 decades, we've been benefiting from this phenomenon, right? Referred to as Moore's Law, just from an observation by Gordon Moore, of course, where we've had very rapid evolution of electronics, but very predictable, okay? So this is just the shrinking of our electronics technology, which has enabled computational performance prowess, right? So back with the Intel Pentium 4004 at a 10 micrometer minimum dimension, to a Core 4 gigahertz processor at a 10 nanometer feature. There is no technology in human existence that behaves this well, that has caused such kind of a revolution in innovation, right? And so I've put some markers on here on kind of some of the big key points that have kind of emerged during this. There are others. I've done this because I think this is interesting from a space science perspective. And then I present this in my radiation effects and electronics class as well, because I like to give people a perspective on what this scaling actually means. So if we imagine the 10 micrometer device being the Empire State Building, today's device is approximately the size of a dog. So the reason we have such computational advantage now is because we can fill up the original volume of that first transistor with a bunch of much smaller transistors, and thereby having computational performance advantages. Okay, so while we have benefited from this, we no longer are really in that paradigm. We've had a disruption, and the amazing thing is we continue year to year having additional disruptions to the market. Okay, so we could no longer shrink in the same way we were shrinking before. We had to have better electrostatic control. So engineers got together and figured out how to solve the hard problem. We went to a more control with fully depleted SOI. Then we needed to 3-dimensionalize the transistor. We went to something called a FinFET. We miniaturized those channels to build, when we were able to control what we call a nanowire, which has evolved into what we're calling a gate-all-around transistor now. And then that's what's being manufactured at present. One of the ways I like to describe this is now when I have a student enter my program in year 1, the technology that they are going to be exiting the program with is going to be fundamentally different. It's no longer that we enter and then all of a sudden it's just going to be 1 or 2 generations advanced and it's going to be a little bit smaller. It's potentially going to be a fundamentally different transistor. Potentially, we're going to be away from a transistors. We're going to be educating on how a qubit works, for example. This is sort of the paradigm we're working. So how do we build something that in the educational and the research environment evolves in the same way? All right, so you're not supposed to be able to read this, but what this chart is if we think about the cutting edge manufacturing facility that can keep up with that sort of evolving electronic platform, while that continues to improve, the number of facilities that can manufacture at the cutting edge is diminishing. So at present, the 5 nanometer node, there's about 3 of those, okay? Okay, so there's all kinds of consequences to this that we could probably have seminars on each one of those consequences. Okay, So that's part one of the landscape. While this is happening, we have less access to the cutting edge, there's less options, and none of those options are in the United States, solely at least. That obviously, from a defense perspective, creates a pretty urgent issue, which is hence the Chips and Science Act and all of the amazing things that we're dealing with now. Manufacturing capabilities are improving in the way of integrating complex devices together. So this is interesting because we're moving from what we call a two-dimensional planar sort of integration of chips, okay, to being able to stack chips and more thoroughly stacking them to involving multiple types of processes. So this is fantastic for us because now there's a market for technologies that are not at the cutting edge. We don't always need the latest and greatest technology. We might be able to integrate things for special purposes. We can maybe take a high-performance gate-all-around device that we're going to, or a neuromorphic architecture, and we can integrate it with a high-power electronics platform for doing communications or an advanced memory architecture. So theoretically, that's where we want to go, and that's the hard problem right now, and DARPA is starting to fund that. So this presents both of these challenges, the diminishing cutting-edge market and the increased integration market, presents challenges for extreme environments. Okay, so that leads me to Radiation Effects Engineering 101. In general, when we think about radiation effects engineering, we start by evaluating the environment, whether that's a space environment, a defense environment, a medical environment. We make a model of that environment, and we project that model into a system. Maybe that system's a spacecraft. We look at the environment inside that spacecraft where all of the electronics reside. We do some analysis of how that radiation, in this case, impacts the device, and we look at individual transistor responses to that environment. Then we will build models that describe that behavior and propagate those up to circuits and systems. At all levels in this hierarchy, we need to do experiments, and so we have to do those in an accelerated way. We can't just put everything that we build in space to test them. So if we use, for example, what's called a heavy ion, which is a pretty common form of ionizing radiation outside of the Earth's atmosphere, there's only 4 facilities in the United States that can give those to us right now. Okay, those are at Berkeley National Labs, Texas A&M University, NASA Space Radiation Lab at Brookhaven, and now MSU, the FRIB facility. Those are the 4. That's all we get. When we do these experiments, we're going to take some data, we're going to pair those with models, and we're going to make predictions of the rate at which we can expect errors. There's all kinds of things we can do in the middle there, and that's where kind of our laboratory at IU has programs involved in all of these, as well as in the integration of these, and then separate programs just even for doing workforce training and radiation testing. So when we discover there are issues with our technology and their performance in these environments, we sometimes need to go through a process of radiation hardening. So radiation hardening, kind of 101, can be thought of maybe as a three-tier approach. Number one, you have your first line of defense is the process itself. How vulnerable is the innate process that you've manufactured your devices to the environment? You're getting less and less choices. Remember the chart of diminishing manufacturing options. Less and less choices for process. And when we talk about, say, space and defense market, you're talking about maybe less than 1% of the total market share. Right? They're not going to change their process to meet our needs. Okay? So then you might have to go to radiation hardening by design, where given a fixed platform, can we do something at the circuit, the layout level, or maybe the system level to mitigate those effects. So that is sort of what we study that process in the laboratory and design solutions at those levels. Okay, so big picture, state-of-the-art chips are incredibly complicated now and may include three-dimensional integration of devices. The most sensitive devices within an architecture like this can hold a handful of electrons to store, to represent the data. They can be very easy to manipulate or corrupt, for example. So these sort of present the fundamental challenges at bay, right? It makes it for a very interesting research environment, but pretty poor for assurance. Okay. So radiation effects engineers have pretty good job security right now, I would say. However, when we think about securing our systems, we have a big challenge ahead of us. Okay, so maybe an example of that in a picture form. What we're looking at here is the leakage current. So this is current, unwanted current, following exposure to some amount of radiation. So as we are absorbing radiation over time, our performance gets worse and worse, and we start kind of leaking current in an unwanted way. That's a common occurrence. So the higher the value, the worse off you are. As we saw that sort of standard Moore's scaling, we actually saw an improvement in that response. For a long time, we had this benefit to know that as we advanced our node, we were going to have a little bit better radiation performance. And then all of a sudden, there's the disruption. We were no longer benefiting from that. We were benefiting computationally, but for these extreme environment applications, all of a sudden, we had a challenge ahead of us. If we look even more advanced, ultra-thin body devices, even worse for radiation effects. If we look at those nanowire devices, some literature suggests that it's quite bad, and some literature suggests that it's quite good. The verdict's still out. We don't quite know. There's probably lots of inconsistencies in how these data are presented and how they're measured at present. All right, so what are we going to do about it? So the technology is evolving rapidly, so must the education system, and thereby the workforce development strategies that we have. One interesting thing is about Luddy is that this is where I think that the asset of Luddy being a 7-year-old, or the Intelligent Systems Engineering program being a 7-year-old program, is that while we don't have the legacy of a 50-year-old microelectronics program, we also don't have the weight of a 50-year-old education system that we have to go by, right? So we're really thinking about that from in a way such that allows us to be as nimble as possible. So it really creates some unique situations. To put this into numbers, latest estimates from McKinsey say by 2030 we're going to have a shortage of 300,000 semiconductor-based engineers in the United States alone, 90,000 skilled workers missing. This number just keeps ballooning, by the way. The last time I looked at this about a year ago, this was about 160,000 estimate. Right? We've known this was coming for a while, and the problem just continues to get worse in front of us. So we need an ecosystem, not just a process. The process is not working exactly. There are elements of the process that work and that we have to retain, we have to embody. That's the engineering philosophy, but we need the ecosystem. We need diverse roles. We need to be able to naturally evolve. We need to adapt to changing circumstances. So right now, to give you a snapshot of the program at IU, IU Center for Reliable and Trusted Electronics, we are pretty diverse as far as our funding goes, as well as its strategy on how we tackle this. We have several basic research and discovery programs. These are mainly funded by, for example, the National Science Foundation, the Defense Threat Reduction Agency, as a part of a major consortium that's centered at Penn State University, the program. We take findings from that and we move them into more applied research domains funded by NSWC Crane, AFRL, NASA, for example. And then we have active programs trying to take that maturing technology and move it into the community. And so we use direct relationships with manufacturers, for example. I'm going to give an example that we're working on with Skywater right now through small business innovation research grants, for example, with Reliable Microsystems, which now has an office just a few walking distance from here. CFD Research Corporation, Missile Defense Agency are all active. We are already operating at about a $3.5 million research expenditure in the center, and that's expected to increase potentially by 2x within the next, say, 2 to 3 years. So the rapid part is there, certainly. What we hope to see happen is the evolution. Okay, so this is a data dump. I don't intend you to read all of this, but what I wanted to do is put it into one place, some of the statements made from IU about what we are trying to do holistically about this problem. Right? You heard this big announcement about the $111 million investments. What is that going towards? About a quarter of that, a little less, is going into staffing. We're trying to attract the latest and the best there is in microelectronics, especially in extreme environment electronics. That is sort of seen as our niche capability, and that's where we're going to put energy. So that strategic environment application. So the Provost has a Faculty 100 hiring initiative. About 25 of those have been identified for areas related to sort of these defense initiatives, not necessarily just microelectronics, but nanotechnology, artificial intelligence, machine learning. We just 3 days ago announced that 5 of those are going to microelectronics design to be directly affiliated with the center. About half of these dollars are going to improving facilities and laboratories. $10 million is going to be invested into augmenting our seed funds from NSWC Crane and rolling out the center. And then the rest of that essentially is for new degree programs. So this isn't just research and innovation, it's going to be paired with educational strategies. The first is a master's degree in microelectronics design, for example, and then you'll see a nanofabrication degree come out. So our early construction of this model sort of thought about the academic, the government, industry partnership. And so we first penciled it down as kind of this this Venn diagram looking thing. But really this is what we'd call a triple helix model. It's about thinking about in a clever way these interaction points of these overlaps. And so you've got the defense, the industry, and the university thinking about the innovation and the research and development and moving that, advancing and maturing technology and getting it out into the work, getting it out into the community, cycling back and looking at the policies and the priorities that are being defined by the government and how that is playing a role, and then how do we cross-pollinate that? How do we train people earlier? So as we've developed it, we've kind of found these 4 main pillars that we're sort of tackling. R&D is at the center, but it's not the 100% focus. Almost equally, we are working on workforce development. So I would say 50% of sort of the effort is going into building clever strategies for attracting people earlier, retaining them, and training them. It's not in radiation effects engineering. We're finding more and more students at undergraduate levels are becoming ready to enter that space. It's no longer masters and PhDs that are just coming out of the programs. So this is driven by findings when we consider things like policy and how to actually develop those in practice. So we formed a group, we're calling it a COP, or a Community of Policy and Practice. We're working with SPIA, the School for Public Policy at IU, and they're doing really clever things. We're looking at real barriers to entry in microelectronics, tackling current opportunities, working directly with the government on identifying policy priorities and how that impacts us at the university and in industry. It's a really interesting element of what we're doing. And then at the end of the day, how do we take our innovative findings and developments, and how do we move them into the industry to develop ready solutions that have high levels of trust and assurance? So currently we have 4 main capabilities in fault-tolerant microelectronics, artificial intelligence, and machine learning. We both in the radiation effects and microelectronics area use AI for helping us learn something about the science that's going on, but also we are worried about their performance in the extreme environments, the integrity of these systems. So we have kind of a 2-tier approach of how we are using that in our domain. We generate experts in radiation testing and analysis. We are called upon by several DoD groups now to vet new facilities, for example, as well as to do on-site training at facilities. So not only are we training our own folks, but we're doing current workforce training. So those that are currently working in the field, we do a lot of work with them to try to get them to be more efficient at what they're doing. And we have some security and trust projects as well. In the next coming year or two, we're going to be tackling more heterogeneous integration problems and building capabilities to allow us to get closer to that cutting edge emerging technologies solutions. So I like to think about this as innovation and research, but also in education and workforce development. We do a lot of really fun things to try to get young people involved. Here's a picture of a team launching a suborbital high-altitude balloon experiment, for example. So we have STEM programs at pre-collegiate levels, certificate programs rolling out in radiation testing. We're working with the physics department right now to do a radiation certificate, sponsoring apprenticeships. We are rolling out new coursework every year at both the undergraduate and graduate level. And we're sponsoring projects not only within our own university, but outside universities. So we have several additional university partners that we are directly sponsoring. And then finally, we care about interacting with the community. So the experiential learning part is a major part of this. This is how I find a lot of young people especially find ways to get involved and are more engaged with what we're doing. So for example, here's the team that launched a high-altitude balloon. These are images that they took on cameras that they built. In fact, when my students first tried to do this, they went to commercial folks, for example, bought some cameras from GoPro and tried to fly those, and they failed because the environment was too harsh. So they went and we designed it ourselves in the laboratory during a course, and what you're seeing are images that the students made with their own product. And so that's evolving. We're launching another one, for example, in April during the total solar eclipse in Indiana. So that's bound to be a very interesting project. Each time they develop something new and innovative to add to this, it's really exciting. But we have also very industry relevant experiences. So we had a student team for a couple years develop a software platform, for example, that I mentioned earlier. There's 4 heavy ion facilities that are available to us in the United States, right? That's it. So the Missile Defense Agency has figured out that estimated that there's roughly 5,000 hours of beam time shortage across the country right now. So to put that in perspective, it usually costs between $2,000 and $7,000 an hour to run that beam time. There's a 5,000 hour shortage, and that's just because there's only 4 facilities, they can only meet so much demand. And in some cases, they have found that upwards of 50% of the time that's actually being used is being mismanaged. Okay, that's a really big issue, especially because the space and defense community for decades have used those facilities, but now we have a bigger commercial interest as well. You know, the dual purpose of the technologies is interesting, but now we have SpaceX launching 60 satellites every 2 weeks. They're testing as well at these facilities. You know, the demand has rapidly increased. So we built a software platform to help Missile Defense Agency organize this time more effectively. There's lots of ways to use these facilities, and we're trying to become more efficient at it. And so they developed this software platform during a capstone experience, and then we were able to create some intellectual property and license this, and now we're licensing a third-party company to utilize this tool so that we can deploy it to the Missile Defense Agency. Anybody that will use it, their program's called Deceptor, so potentially, you know, the tens of thousands of hours that need to be run will have to utilize this tool. But we also have done a lot of work training people that are using on-site these facilities. Last time we went, last month, we had a 16-hour experiment, and we ended up running 22 beam hours, and that's because we go and we're effective at it, and we can use the time, and those data hours are important. And the large company that was behind us wasn't ready for their experiment, so they gave us the time. So we're trying to fix that problem by training folks on how to be more effective. And so we built an emulator that allows people to train in real time what the experience would be like. And we're partnering with Vanderbilt University on deploying that emulator, for example. And so when we do these experiences, we call on the community to talk to our students, right? So my students will sit down with the engineers at Berkeley National Lab. We'll get some engineers at NASA and at JPL to come and talk to them during their preliminary and critical design reviews. So that's a really big part of the workforce development efforts. All right, so I think I've got enough time to kind of talk to you for the remainder of this time about one particular example of some of the innovative research that's happening in our laboratory. I can't go over all of it, so I really limited it to one that I thought would be interesting and relevant to this community. So one of the things that we do is end-to-end design through deployment. So we are designing, fabricating, and testing in their laboratory. So that means design for evaluation in extreme environments, to the realization of the physical silicon, to the development of the electronics platforms that we go to take to test and eventually build rad-hard solutions out of. And so we've developed this sort of iterative approach at design, model development, and release that we've instilled. So this is a very engineering-like approach to the problem. But what we've done is injected this with kind of student and workforce engagement along the way. So for example, right now we have a partnership with Skywater. You know, they've got a sticker out in the lobby I saw on my way in. Skywater has been a critical partner. They're right now the only pure U.S.-owned foundry that is currently sitting at a 90 nanometer technology node. They both have the bulk silicon low noise 90 nanometer as well as a rad-hard 90 option that they're trying to develop. And we have been contracted by Skywater on what's called the NSWC program to help them understand what we call random telegraph signal noise. It's a type of noise that's internally generated because of defects in the process. Most of the time you don't really care. These defects actually will trap single electrons at a time, right? It's like, well, why do I care about a single electron getting stuck and then released periodically, right? In most applications you don't, except when you talk about extreme environment applications where we have really low noise, for example, imaging application where you have low noise requirements. So in fact, we would supercool these devices down to 45 Kelvin. We've actually tested these all the way down to 4 Kelvin temperatures, and so that we can understand how problematic, how common are these defects, and to try to at scale. And so the focus of what we tried to do is improve both their spatial understanding as well as their temporal understanding of this problem. So we designed a custom solution. Most of the time, the state-of-the-art way to do this is you take a device and you have a very low noise measurement equipment that you have to do a single device at a time. And we said we can do better. And so we built an on-chip architecture to try to measure these single electron like defects. Okay, so we're trying to measure one electron at a time at scale. Okay, so that's kind of the scope of the problem. So we came up with a solution that had about 20,000 devices that we can scan through and search for these sort of defects. And so this is what it looks like. It's called DOE1C3, not a great clever name or anything, but we have this sort of array, and it really mimics what you would call a readout integrated circuit. So the kind of circuit that sits behind your camera that would take your individual pixels and turn them into electronic information, but specially designed such that we can isolate and measure these sort of electrical signals due to these defects. So we did that, but we did that with every possible transistor variation available in the technology. So every option with a lot of different types of size variations as well. And then we built a measurement apparatus around this thing in order to be able to characterize this sort of noise phenomena. And this is how this evolved, right? We started by just taking our die, packaging it, building a little breakout board so that we could measure it. Then you can see a student's prototype board come out of that. Once that was verified, we built a more enclosed solution that we can have high fidelity measurements with. So what we do is we'll kind of run a pre-processing scan to quickly kind of get a cursory view of the chip, make those measurements, and then when we do, we'll run a full, complete scan of our chip where we gather all kinds of data analytics out of that and then can perform some statistical analysis. So this is kind of an example for those of you that are circuits people in the room. If there's a few of you, if you're not, don't worry too much about it. I'll give you the 30,000 foot view. But we have a device. We're trying to measure imagine the defect is that red dot on the screen. There might be one of those, and that one defect causes a single electron to be captured. We're trying to measure that. So we built this this is a simplistic view of how that measurement works. Okay, that's all this is on chip. At the end of the day, what you get is this sort of time series where all of a sudden when that electron is captured, you get an instantaneous change in the signal, and then it drops back. And so whenever these defects happen and are active, you end up with a messy signal like that. All right, so what we did is we did it at scale. Remember, it's not about that one measurement, it's about the 20,000 of those measurements so that we can gather some confidence in what we're doing. Well, this is an example. The student who happened to be the student that I showed you at the very beginning, his picture in the newspaper. He made a measurement of that kind of light purple area of the chip. If you imagine this being our chip, each one of those little dots is a transistor on the chip. He scanned through that little section, and all the little yellow symbols are where he detected one of these defects that captured an electron. Well, you expand that pixel up and you have all these really interesting analytics that pop out of it. So we take an understanding of that, and that's where then we can tie into the physics. You know, Skywater loves that because they can take that and build that into their models. And so what's happening now are these data are going back to inform their development of their process design kit, which gets released to every single customer that Skywater has that buys 90 nanometers. So after that, we also, of course, that's a reliability problem. It had nothing to do with radiation effects. We also want to know how does this technology perform in a radiation environment. So we took these devices and we wanted to measure that at a facility. But there's a second problem I mentioned earlier. There's only 4 of these facilities in the United States, and the government cares a lot about the use of this time. So I talk to the DoD and I say, I'll train students on site and I'll also test product that may be of use to you, right? And so we took our part and we did a preliminary look at radiation vulnerability of this process. We had 3 PhD students running the show on site. I think it was 3, maybe 2. And we brought an undergraduate trainee with us, one that only knew the word radiation out of the problem. So we took them to Texas A&M. Here's some pictures. There's some fun ones in there. So these are all students. There's one of the guys at JPL standing there with me and various students that are presenting the work and our experiments. And in this picture, there's one of my students asleep under the desk as well. So sometimes these last a long time and are very grueling. And then, of course, there's Jay that's very proud of his experiment that's sitting there. That's that same Skywater proto board. And then at the end of the day, we isolate this thing that we're going to measure, and we evaluate the response to radiation. What we're looking at here is the amount of area on the chip that's sensitive to the ionizing radiation that we're trying to measure versus the amount of energy that radiation imparted into the device. What you would normally expect is at some point there would be a vulnerability. There would be some amount of the chip that's vulnerable to the problem, and then eventually it saturates. So this is very well characterized radiation effects of the process. And in fact, what we showed the customer in this case is that this particular amplifier is radiation tolerant to most near-Earth environments. We could probably take our op-amp to a geosynchronous orbit, and it would survive for 5 years before you ever saw an upset, for example. So, we do training, but we find really great things that we can put into the community as well. So to kind of summarize where we have come over a very short period of time, this last year we have developed just a whole array of very active collaborations. This is not happening in a vacuum. It very much requires community support and interactions with all of you. So we, from the local industry that's interested in being present here at Westgate, to our government sponsors, to our other universities that are nearby that are involved in amazing research. We're actually involved with Vanderbilt in two ways. We do a basic research program with them, but with another collaborator in geosciences, we have just been awarded a spacecraft mission called Pulsar. It's a NASA spacecraft mission. We're measuring ice cloud formations. And so that was just announced about a month ago. We've been involved with Purdue for years on workforce development, Arizona State University, and then some of our small businesses to help us get our technologies, helps kind of put IP around our technology and get those into the community. So the one thing that I want to note out of all these sort of like these data, these metrics maybe, is our number of internships in workforce development that are kind of happening. I know I talk almost every day to somebody that says we need more people. Last year, everybody in my lab had an internship, almost everybody, so 7. This was actually somewhat of a problem for me. My entire lab was somewhere else over the summer. I had a hard time being productive. But it's a good problem to have, but we're putting all of our students somewhere in the field. But we're increasing that added value through strategic partnerships, right? The plus 18 that's on here, that came from Reliable Microsystems, for example. So we have partnered with them more poignantly now to say, can we leverage this and move some of our students through this pipeline? Can we have your engineers train our students? And clever interactions like that. So overall, we had about 35 new people just this year learn about radiation effects in microelectronics. Right? So this number is what I hope to see increase by about 300% within the next 5 years. It's sort of my target number. So I'm hoping to see about 100 of those at IU. I think we're going to get there based on these early days, but that's where we are. So at the end of the day, you're welcome to contact me directly as this evolves, as more information emerges. And with that, I very much appreciate you being here. This is very exciting for me to see the community come out for this, and I'd be happy to take any questions. We'll go with you first. Very nice question. The question, I'm going to summarize the question so that everybody can hear it. So the question was that I identified that we have 4 major heavy ion test facilities relevant to single event radiation effects in microelectronics, and that's somewhat of a bottleneck. How does that compare to globally? The short answer is that it's not a good outlook. Europe is doing a lot better. I just had, so my radiation effects class in microelectronics at IU, we had our last class today. And one of the things I do in that class is I kind of do radiation effects 101. I did a 1-slide version for you today. I do a half a semester version of that on campus. But the second half, I let the students decide what we talk about. And so I teach them how to interrogate journal articles, and we talk about new topics. And the one that was today was all about CERN and all of the amazing radiation test facilities that they have at something like 20 giga electron volt protons, for example, which is non-existent, I don't believe. The only thing that comes close is at NASA Space Radiation Lab. But what they've done in Europe is built what's called the RadNext program. Luckily, we're well affiliated with them. We know them very well. but they have a European-wide network of these facilities that are cropping up, and it's not just that type. We need multiple types. We need, we've been leveraging medical proton facilities for the last decade pretty heavily. Occasionally we'll go and test at a site that they will also treat people that have cancer, right? And not all companies are amenable to this, right? You don't want your cancer patient to be sitting next to a PhD student, microelectronics engineer that's trying to blast their circuits, right? And so we will test in the middle of the night because we need that data point, and there's not many facilities. It really is a staggering issue. Europe has invested a substantial amount of money toward this. That being said, there are major initiatives right now out of the Department of Defense that are trying to help this problem. So the national laboratories, these radiation facilities are kind of Department of Energy, but DoD obviously has an invested interest in this. And so DARPA right now has a call for innovative radiation test sources, more compact, higher energy. They're asking for everything, higher energy, but also smaller. And that's happening right now, though. And those players have been announced. They're also now trying to tackle the problem by having more innovative kind of coupled modeling and hardware solutions. So how much can we augment the data with modeling, and how much can we trust that? That's a big initiative happening right now. And then just this week, there was a request for information from the Missile Defense Agency to help identify potential solutions to this problem. That sort of is another way to describe the urgency of the situation, right? Because we're really not doing that great to that respect. IU used to have a cyclotron, and at that time there wasn't a great understanding of this potential market that was going to happen 15 years later, right? So we're trying to do what we can. We're funding our low energy neutron source to outfit itself to help, because that's another data point. It's not going to give you everything you need, but it gives you a data point on that curve, and every data point is important for us right now. I think there was a question over here.
Yeah, I was curious, your faculty that you're attracting, I was under the impression that a lot of our manufacturing chips, integrated circuits went overseas. Does the U.S. still retain a leadership role in innovation and pushing these chips, into greater capacities, or is that, where are we in a global perspective in terms of innovation and research in the integrated circuits?
So the question is, where are we globally in the innovation of manufacturing capabilities, essentially? You're right to note that a lot of the manufacturing is overseas. So if we go back to the chart where I just charted the number of facilities versus the cutting edge technology node, that diminished down to 3. And that's because the capital investment that's required every year and a half to 2 years is exponentially increasing, right? It's something like $50 billion just for the latest fabrication facility right now. That's probably $150 billion next generation, next node. That's the reason that the issue exists. And so, 85% of the market is at TSMC, Taiwan Semiconductor. So that's the majority of the market. That being said, a lot of those companies are being incentivized to have a United States presence now. And so the CHIPS and Science Act is the attempt to move the needle for that problem that you correctly identified. So, we have ARI leading the Microelectronics Commons Hub here. And so that's helping kind of churn as part of this major ecosystem. And so that's super exciting for us regionally, and will help move the needle nationally. There's a few other of those. Many of them are investing now their private money into augmenting that CHIPS and Science Act money. And so we are seeing action there. I would say that most of what we're probably going to have a benefit of is the fact that we are moving towards more advanced packaging solutions. It allows the market opens up a bit, right? We're not only dependent on that cutting edge node that maybe just gives us more computational edge. We also need niche manufacturing. And so there's been a lot of more focus, I would say, in those niche nodes that may not be at the edge, but are going to be playing a bigger role in especially as we see more complex integrated systems.
True or false? Are we producing only about 10% of microchips that we need in our country?
The question was, true or false, are we only generating 10% of the microchips we need in the United States? Unfortunately, since you gave me a true or false, that it's going to be really hard for me to get that right. So that's probably a good estimate. 85% of the market, maybe more than that now. It's probably closer to 90% of the market is TSMC. The other 10% is not just United States. Okay, so that's probably not. I bet it's even less than that. If I was, I don't want to bet on microelectronics though, for a lot of reasons. To see kind of the evolution of electronics, it's amazing to see, how this advancement has sort of morphed into these really amazing solutions, the technologies. You really don't know how that's going to turn out.
My granddaughter's husband worked for Micron in Boise, and they're already under construction with their new facility for the production of microchips. How far along are you here?
How far are we in Indiana?
Yeah, is there going to be a facility built to produce microchips that is sold? How far into the future?
Yes, that's going to happen. Absolutely. Somebody else that's here probably could answer that question better than I can about when, but I believe they're breaking ground soon. Yeah. Yeah.
I got to take a tour of Micron in Boise with my granddaughter's husband. It's quite impressive to watch the production.
Yeah, they're amazing facilities. Yes.
Which focus areas within the supply chain are you thinking that would be most complementary to the actions currently going on in Indiana? There's the microelectronics, and then there's the packaging, and there's other components that go around it as well.
So to summarize the question, which portion of sort of the supply chain would be maybe most beneficial kind of regionally? So that the trusted supply chain in particular is a complex web, and it morphs constantly. I think what we hope to see happen with a lot of these national investments is that more of that trusted supply chain can be localized. I think that there's going to be a lot of advances in advanced packaging, and I think that would be a huge asset regionally. I think that we're going to have to see elements of from lab all the way to fab to deployed solutions. And so, I think the more low-hanging fruit's probably on the design side. But if we can solve some of the advanced packaging problems, especially locally, I think that would be a major asset. Do we have time for another one? Okay, I think we got one more.
You mentioned you licensed something that you guys innovated. Collaboration is so important. How do you balance the collaboration versus the interest in having those discoveries for individual organizations? How do you information share and collaborate?
Yeah, that's a very nice question. So how do I balance the collaboration, the generation of IP versus sort of the, in an academic setting, we like to publish our works. So there's absolutely a balance. I push all of my students to publish pretty hard. And they're probably giggling about that right now when I said that. But you know, they are also all reporting to somebody outside of our organization. So it's interwoven. It's not a separate activity. The collaboration is just a fundamental element of what we do. Sometimes that collaboration results in intellectual property that we want to retain, and we'll retain part ownership of that. But that's, you know, that's not the business model that we depend upon. You know, that's the nice thing about being involved in a research center and not, you know, where if I was a small business, I might have to think about it a little bit different way. Instead, I'll partner with small businesses wherever our discoveries become important for the industry. It may be that I need to disseminate that rapidly and make that open source, and we'll publish that material. Maybe the right way to do it is maybe if it's more applied, we'll go that direction. And so I don't know if that exactly answers the question of how that is balanced, but I would say that the collaborative nature is just ingrained into my philosophy of how to run that. Right? It's not a tangential activity that we seek out. It's fundamental to what we're doing. Thank you.
Thank you, Dr. Lovelace. Let's give him another hand. Thank you so much. That was so much great information. Obviously, I'm not into the technical piece, but I understood a lot of it, so I hope other people that did. So I have to just mention that the last 4 to 5 months, when we've had a concentration on microelectronics, if you've been here for the first Tuesday events, we have had grad students, research students, undergrad students from multiple universities that are around the region. So I want to acknowledge the ones that are here tonight that Dr. Lovelace had probably encouraged heavily to be here, I'm sure. But if you can stand up, and we can give you guys a round of applause as well. I think we have to appreciate not only the intellect of you gentlemen, but also the passion that you have and the appreciation for what's going to be happening here and what you're going to be helping support. So thank you for doing that. So I want to thank you all for attending tonight. I thought this was a great presentation. We also want to let you know that it is being recorded. It was recorded. And the slides will be available. So for all who have registered, we will provide that information to you. If you did not register for the event and we do not have your email, make sure you contact Morgan Tavis over here. She's the Marketing Communication Manager, and she'll make sure that you get those. We will not have a first Tuesday in January for obvious reasons, but in February and March, we have some energetics discussions that will be had. And then in March, we will have Booz Allen Hamilton will be speaking. So, and we'll just continue all those discussions in the thrust areas of the defense, and hopefully they'll all be relevant and made aware of what's happening within the region. So check our website, which is the westgate-academy.com website. You can see more of the future events going on. So again, lastly, we just want to thank Booz Allen Hamilton for sponsoring the networking event that we're going to be happening outside of the lobby here. We certainly want all the conversations to continue. I know Dr. Lovelace is going to stick around to answer any other questions that you have. So again, thank you for coming, and let's go have some light refreshments.